about high energy gamma ray astronomy that was published this year. Also, Thomas Lara and Elena did a very wonderful review paper on LID effect, actually, gamma rays. So, if you are interested in this topic, you can have a look at the different papers of this special issue, because I think you did really well. Okay, let's go now into the sources, and let's have a look at the extreme universe. We have seen gamma rays are not thermal. Okay, so we need to look for non-thermal phenomena, and usually this is called the violent universe, the extreme universe as well. There are, as usual, many ways to see the same thing. These are different representations of a gamma ray sky. So if you ask someone, can you show me a map of the gamma ray sky? There is not a unique answer. You might be interested in the low energy map, in the high energy map, in the variable sources map, or in the steady source one. So let's see what are the different ways of representing this gamma ray sky. Starting from the low energies, I have not described it in detail, but at low energies we have the integral satellite that works like basically a mixed satellite with coded mask. And this is the sky covered by integral in the last 21 years. So it was mostly focused on the galactic plane to study galactic sources and lines, because still there are lines that you can detect at these energies. And in total, this sky is composed by 2,400 sources. Okay? And there are a number of different objects emitting this gamma rays. Coming now to always low energy range, so below MeV. This time we are looking, what are we looking at? It's written there. What is this? For this move down to there. Oh, what are there? The gamma ray burst sky, okay. Gamma ray burst sky means that here what is plotted are only the gamma ray bursts detected mostly by GBM of Fermi, the scintillator, the wide field of view one that are operating in the low energy range, but also there are other sources detected by LAT and by SWIFT, that is a lower energy satellite. So in total, in the last, this is a map from 2018, 14th of February, on Valentine's Day. I don't know why to do this map. That's so romantic, but okay. And you see that, well, the distribution of the incoming direction of this gamma ray burst is quite uniform in the sky. They are extragalactic, they come from whatever direction. And for some of them, we have a superposition of more than one instrument looking at the same gamma ray burst. Probably because GPM gave the alert and LAT pointed looking at the same direction to see the high energy tail of this emission. Now let's see the high energy sky observed by LAT. Here we are, high energy range means between few MeV up to 100 GeV. Okay, it's the highest energies that can be visible by satellite. And also here you have more than one way to show basically the same thing. This is the usual map used by astronomers. For example, when we build the multi-wavelength Milky Way, we were looking at these maps. It's nice, but you cannot really by eye see which are the sources, right? It's to have a full overview of the sky, but still to have information about the sources. This map that is quite crowded is much more useful. You can see here that the last map counts a lot of gamma ray photons, okay, individual photons, for a total of more than 5,000 point sources. Plus, you have the diffuse emission or the highly identified sources that are into the counting of this map. And now let's focus on this map that is the 4FGR catalog. In the tutorial, we will try to see how we can have a look to a catalog. What is a catalog? And in this case, we have a question. Association this one. So association is that you do not have a counterpart in other wavelengths. Okay, so you see that there is a gamma ray emission there, but you do not have or maybe you have more than one, so you are in doubt on which in the field of view can be the emitter. While unclassified means that you have a counterpart, but you do not know. You are not able with the microwave information that you have. You are not able to understand, for example, if it is a laser or a radio galaxy. It happens very often, especially in the Fermi map, because we have low emission sources, and so it's quite difficult to disentangle between models. So this is the reason. And the number of unclassified and not associated sources is really large. Look at the boxes. You have a lot of sources from which you still do not know the origin. And there is a huge work in the gamma ray community to try to identify the source, but it's difficult. You have to do all the associations with the other bands, build the spectral energy distributions, and ask yourself, does it make sense or not? And then you try with other sources in the same field of view. So, and sometimes you are wrong. Sometimes you have early associations that become wrongly associated. So, yeah, this is a stronger work that is quite demanding in time of, especially with these numbers. You see, we have really a lot of sources. And the sources are of different origin. Basically, we have many sources in the galactic plane that are pulsar, binary stars, supernova remnants, and then we have the extragalactic sources that are in large majority active galactic nuclei. Now we go with our feet on the ground. We are looking at the very energy sky, so we are using ground-based telescopes. In this case, the map is superimposed to the last map we have seen before. So the TV sky is only the dots. What does it tell you? We don't have many sources, right? It's really fully populated. And in fact, we have less than 300 sources here in total, and less than 100 extragalactic. But of course, we are looking at the most energetic photons that we can detect, about 100 GeV. So the fluxes are low, and the number of sources that reach these energies are less. Simply, it's like the cosmic ray spectrum. You have less and less sources emitting at high energies. This is somehow expected, right? If we want to see at the very recent map on the ultra energy range, this is the best we can do. This is the LASO map. It's just populated by a bunch of sources in the galactic plane, but that's because this is an earlier release of data, just after a few months of data. These are the sources we were looking at, photons, no? The highest energy photons, the table that we were looking 2 days ago. But as I said, LASO has just started the operation, still in construction actually. So we will have, in a few months or years, a better idea on the ultra energy sky. But probably, as we will see today, unless there are some unexpected effects of quantum gravity or actinolite particles, probably the LASO side will be focused on the galactic plane. You won't see any extragalactic source because these photons interact and cannot reach us. But who knows? Let's wait for the data to tell us also. So, having a look at the gamma ray zoo, I've divided the sources into 3 big families. We have explosive events like supernova explosions, gamma ray bursts, I've heard this many times, and novae as well. These are galactic objects that can emit gamma rays in a recurrent way. Then we have galaxies. Most of them are active galactic nuclei. We have doubts about AGNs, but they are, or it's clear to you. So, AGNs are this supermassive black hole at the center of each galaxy, accreting material, and in 10% of the cases, you have jets. Okay? And you can already imagine that these AGNs emitting at gamma rays are the ones with jets. Because in the jet, you have most of the acceleration of the particles. And then in the galaxy family of gamma ray emitter, you also have starburst galaxies, because in this case, the supernova rate is so high that you can see gamma rays from supernova explosions even from outside our galaxy. It's a matter of statistics. Finally, the third family of gamma ray emitters, we have dead stars. Supernova remnants, pulsar, and accreting binary stars. So in this case, these are mostly the galactic objects, right? Yes, radio galaxies are AGNs seen from the sky. Because you see the 2 jets, mostly, but they are really laser from another perspective. They are the same object. Let's look now a bit into detail in this family, especially trying to focus on which are the observables that we need to study them. For explosive events, let's say you want to study gamma ray bursts, because it's more correlated with multi-messenger connection, and that's the focus now of our community, right? So what do you need to study a gamma ray burst from the experimental point of view? First of all, you need to catch, right? So again, you need some instrument that is patrolling the full sky and tells you, look, there is a gamma ray burst. Then you go there with the other instruments. So what do you want to do with this gamma ray burst? Which are the studies that we are doing? As I mentioned last time, we are first of all characterizing the overall emission and the spectrum of the sources, like usual. But in this case, what is the driver is the time. Gamma ray bursts are really fast. So you need to have sensitive instruments to fast transit. Because look here, these are light curves. So you have the time here, you have the flux or the counts, the counts per second. The y-axis as a function of increasing energy from QKV up to about 1 GeV. This 20, you have 0 here, and this 20 is 20 seconds. So all the gain of the prompt emission is made in 20 seconds. If you want to do a spectrum of this guy, you have to be there very soon, and the spectrum will change in time because the emission is changing. So you want to do many spectrum and see how the emission changes over time. So these are the main driver of our observations in this case. We try to collect as much photons as possible to build the spectra as a function of time and try to model what is operating, what is producing these photons. It's clear?
In order to make studies, they are going to correlate the lower median and the 10 seconds
well, this plot is really from Untitled Chapter. So it was done only with the last data that was there in the field of this system. But the problem is that you see, you arrive at G. In case that you want very energy observations, then you start observing usually here after 1 minute, and then you can catch something after blue phase. But for the prompt, well, this is a challenge for the next generation of students, trying to be there as fast as possible, or have a field of view large enough to catch a gamma reverse. But in a field of view, how large is the moon? Your hand, you remember? Yeah, yeah, or it's less than 1 degree. If you can cover the moon with your finger, and the sun as well will do that. But they are, doesn't think so, no? But when you try, it's like that. So again, this is 1 degree. The field of view of Cherenkov instruments, the high energy one, at the moment is 4 degrees. So it's like that. What is the chance that you get a gamma reverse from the direction that you're looking at? It's pretty low, because it's very tiny, your field of view now. In the future, we will have larger field of view, the chance will be higher. But yeah, sometimes you have to be lucky. No, not only. Okay, this is. Now the galaxy class, and in this case I will focus on blazars for their, again, multi-messenger connections. Blazar are the class of objects we were talking yesterday when we were speaking about the correlation of the neutrino with that flaring blazar. It's that one. These are active galaxies with the jet pointing to you. In blazar, well, they are persistent emitters. What does it mean? That some blazar emit gamma ray, usually always emit gamma ray. Still, this emission is variable, it's highly variable, depending on the class of the blazar. Of course, there are some divisions, but even in blazar, you have variable emission. So, what will you study from blazars? Again, you have light curve and spectrum. I'm showing you again the neutrino blazar STD, spectral energy distribution. You have the neutrino limits as well. This was the flaring data that were used to model the data during the flare. But there have been other flares without a neutrino associated, so it's variable. In all the bands is variable. The gray, you remember, are archival data from the past, and simultaneous data are colored. So in this case, we are showing a picture in a given moment compared to the picture in the low state of emission, in the quiescent state. So flare, quiescent, another flare, and every time this flare change, of course, and you want to model all of this. What is the time change in blazar? This is, in fact, a very important information because you want to know how fast blazar change so that you are able to get the simultaneous spectral energy distribution in different bands. And usually the typical time scale for blazars is days, I would say. So you don't have to be really there very fast. You have varying blazar under at the minute scale, like in this case, Galactic was flaring, and in this case you have me. Okay. This is a very high energy method, flux about 200 GB, light curve, sorry. And yeah, the variations were at the time scale of hundreds of minutes. But yeah, you also in this case, if you want to study the emission, you need to be fast, but not as fast as gamma reverse. Just to make a connection with the newspapers, blazars are also basic source. Well, active galaxies, sorry, also this source. You have probably seen the M87 image of the black hole. This is a radio galaxy that is also a very energy emitter. And in this image, you see what I'm talking about when I speak about field of resolution. Here you have the radio images down to really a very tiny resolution. It's not quite clear here, but you are zooming out. At every step, you are zooming out, and at the end, all of this with the jet included is included in the gamma ray magnetic when you look at the resolution. So all the black hole, the small jet, the whole galaxy is all inside this spot because we do not have resolution enough to see the details about the jet and the black hole. So if you ask me, where is the gamma ray emission coming from here? Well, we cannot tell you from the image. Maybe we can tell you from the variability argument we see in radio, for example, in which we are very able to disentangle tiny portion of the map. We see a variation, and we see the same variation in gamma ray. Then we can see probably the gamma rays come from the same region. But it is a connection that we do not from the image, but from the variability side. And then we have gamma ray emitters from galactic objects, and in particular, dense stars and their remnants. Here, the crab is a fantastic reservoir of studies because in the crab region, you both have the supernova remnant around and the pulsar inside. And both of them are emitting gamma rays, both the supernova and the pulsar. Therefore, you can study the supernova like with the spectral energy distribution study, and this is often used to calibrate instruments in different energies. It's a pretty stable emitter, at least it was until it was discovered to be variable. Our standard angle is variable as well. There is nothing that is stable, the gamma ray sky is like that. But on time scale of days, it is stable. So we often use to calibrate different instruments in the region where they have the same energy coverage. And then we have pulsars that are fastly rotating neutron stars, and in gamma ray you can also see the pulse. Look at the scale here, millisecond, right? So really, see this pulse, you are going to a very tiny time scale, and you fold the photons, and then you find a signal. These are usually light curves built folding, assuming a period and folding of the data so that you see a signal popping up to collect statistics. After this overview of the different sources, we focus now on the propagation from extragalactic distances. Now let's assume we know that we have gamma rays traveling from these sources, lasers, for example, to us. Now, which kind of interaction it may experience a gamma ray? What is between this laser and us? What is this gamma ray emitting? Think of it. What is filling the universe? The CMB. And then we do not have only the CMB. We have the light from all wavelengths filling the universe. Sure, the intensity of this light might be different. So let's see the intensity and also the probability of interaction. But don't think that the CMB is the only background in the universe. That is not the case. So the process, dominant process that we have that may affect a gamma ray propagation, because we also have gammas arriving to us, is spare production. Okay, we have seen at QGV, this is the dominant process. This gamma ray meets another photon. You will see the energy of this photon, and it produces pairs of electrons and positons. The net effect is that the flux observed from Earth is suppressed by a factor that depends on this opacity. And the opacity itself depends on the distance of the emitter and the energy of the photon. If you go farther away, you will have more chances that your photon interact, because you travel more, you have more meetings, you have more chances to meet another photon. And the energy, the highest energy you have, the highest is the probability of this interaction as well. This Emax is the energy of the other photon needed to do this pair production. Let's see the numbers. So we have a photon of 1 TeV here from a blazar. It emits another photon and it creates pairs. The maximum energy of this other photon, if we have a 1 TeV photon, the energy of the other photon is 0.5 eV, electron volt. Okay. This is the maximum of the probability of interaction. In other words, if you look at the wavelength, it means that 1 TeV photon interacts with a photon with 1 micron. What is the energy of this? Which kind of background are we talking about? What is the background at 0.5 TeV? Photons are those. These are some details if you are interested in this. These are the universe background. We have already seen this one, but it is really full of information and it takes some time to understand it. We have our friend, the CMB, very, very bright. And then we have all the other backgrounds filling the universe. We have a radio background, optical infrared, UV, X-ray, gamma ray. Which is the background at EV energies at micron? We have the answer here. You are in this range, okay? Optical and infrared. So when you think about interaction of a gamma ray photon with the background, the maximum probability that you have for a TeV photon we are talking about, because we were focusing on TeV, it is not with CMB, because the energy is not enough. It is with high energy photons, optical and infrared photons. Okay. Now, this is our current knowledge of the CMB. Something extremely important about backgrounds is when you understand backgrounds, is starting from CMB, because CMB is a perfect Planckian, because it is a picture of a specific phenomenon in a specific time. What happened after that to CMB? Nothing. It's simply diluted, right? It's not the same for the other backgrounds. Suppose, for example, of the optical and infrared background. What is emitting optical light in the universe? Stars, right? Mostly stars. And what happened to the stars in the history of the universe? They were exploding and then dying, exploding again, dying. We are now at the third population of stars. So this light is not an image of a phenomenon in a specific moment of the universe, like the CMB. So it's relatively easy to measure and make models. In this case, we have all the history of star production and dust reprocessing this light. That is the reason of the infrared light. So this is the first reason why it's so difficult to study EBL, because it has a lot of information inside it, also of cosmic evolution of sources. And we don't know much about that. So the EBL actually is a picture of all the history of the optical universe and its evolution with time. Okay? So looking at this EBL really means looking at the photons collected from the first star, but also from the last stars, all together, summed up. Now on this extragalactic background light. First of all, it is 30, 40 times less bright than the CMB. Also, is fully known, in particular in the infrared band. Let's see why. If you take a picture with a fantastic telescope, like in this case it was Kobe, of the infrared light, you see this map. It's not a uniform background, right? It has shapes and bright parts. That's because you have foregrounds. Foregrounds are backgrounds that are emitting in our system. In this case, what is the system emitting infrared light? Kobe is a satellite around Earth. When it tries to look at the infrared light, it has the sun, the galaxy, the Milky Way. This is not part of the EBL. EBL is the extragalactic background light. So when you try to measure this EBL with your instrument, it's not like the CMB, for which you don't have much background noise. It's really, you are full of background because you live in a galaxy, and the galaxy emits optical light. So it's really a challenging thing that of measuring directly with the EBL. You can try to do that. You subtract your background, then you subtract the light from your galaxy, and this is the result. The black part here is just an artifact due to the fact that you have to subtract the galaxy, and then nothing is left. It's too bright, the galaxy, to let some photons left. But still, you will agree with me that you have some doubts about your measurements because the foregrounds are so bright that probably this is really a difficult task. And I'm trying to give you the message that the CBL that we take as a parameter in our photon propagation, it is a full field of research, and it is still now really debated because of these difficulties of measuring it. So now zooming in this EBL, extragalactic background light, you have two peaks. We have studied before optical peak and infrared peak. In the optical band, the peak is at 1 micron. The optical is here actually. And then you have the so-called infrared peak here. Stars are the main responsible of the optical part. Thus, so this optical light is reprocessed at lower energies and emitted as infrared here. The reason for this EBL is 90% stellar activity, but there is also a big portion, 10%, that is due to AGN. Even the accretion in AGN is emitting optical light. And now let's try to compare its current limits on EBL, you have lower limits, upper limits, then altogether gives you an idea on the experimental effort to measure it. And the foreground emissions, what we said before, our zodiacal light. You see, the zodiacal light is at the level of the CMB as luminosity. So it's really dominating with respect to this EBL. And this is the challenge of measuring and then subtracting a background that is much higher than what you want to measure. I will mention briefly how we try to do this direct detection of EBL by measuring directly the light. First of all, in this band, in the 1 to 5 micron region, experimentally, a team of researchers found a hint of peak there, a hint of a rising part in the spectrum. And we found a hint of populating free stars, the first stars of the universe. They were claiming that this was an evidence of the first stars of the universe. But finally, it turned out that it was due to this huge foreground emission that they did not subtract very well. So also, very often from the experimental part, we are claimed that are due to instrumental effects or wrong background subtraction. And in this case, many people was doubtful because they said, very sure that you subtracted the background properly. It's a strong claim that already seen the first stars in the universe. And in fact, it was a false claim. In this intermediate band, where you have a valley in the EPL, you have a peak in the foreground emission. So it becomes even more difficult to measure this background. And in the highest energy band, it becomes more easy to measure the EPL, at least until you have the CNB popping up. And then, again, you have a dominating background. One way to resolve this is not trying to detect directly the EPL, measuring the photons, but studying the fluctuations of the emission that you receive with respect to the average emission. This is just to mention how they do this. But this is, again, not an easy task in this infrared region that is now one of the lines which we would like to be more involved in the next year of the Cherenkov telescopes. Then another way, so you cannot perfectly measure the EPL, or you can try, but it's difficult. You can try these different approaches with fluctuations, or you can try to put limits in some way. One very effective way has proven to be the galaxy count. If you count the galaxy, then you have a lower limit on the total light that is emitted by the galaxy once you assume that the galaxy has a standard emission, right? And this galaxy count, done a few years ago, provided very solid lower limit on the EPL. So it's difficult to measure the EPL. Don't forget that the EPL that we see now is the superposition of all the history of the EPL together. So if you want to go down, you have really a challenge when trying to model how your photon emitted at redshift 3, let's say, your gamma ray, it did not interact with what we see now of the EPL. It interacts with an EPL that evolved during time because the stars evolved. So it's really challenging to model this interaction because the EPL itself changes with time. Due to the fact that you have no stars coming into the game. You see here, this is a recent work done by thermic evaporation, and the peak of star formation is at about redshift 2. This means that the EPL changed a lot and had a peak of light emission, and then probably does also play an important role in the reprocessing in the infrared line. So many methods are trying to model the EPL, starting from the data and then going back in time, or starting from hypothesis and trying afterwards to match this hypothesis with the data. There are really a lot of EPL models. These are the three main classes: empirical models, physical models, and other models. Also here, there is a review in this universe issue that if you're interested in, it's very informative. And this is an example of what this model gives to us. Let's take, for example, one of the most popular models, Franceschini. The other one is Dominguez, that is very much used in our community. So just meaning try to fit, to model the current EBL. Then he proposes an evolution with time that is needed to compute the absorption factor. This is the factor that goes into our suppression. And it is a function, as we said before, of redshift. Different lines represent different distances of the source and a function of energy. The larger the energy, the stronger the suppression of the flux is. We see it better here when I'm plotting the tau, no? According to this model. So this is let's have a look. We have absorption factor, that is the factor here that we use to compute the flux that we can observe given unlimited flux. Let's focus now on a nearby source, the red curve here. For a nearby source, this absorption is not effective until here, let's see, when it is 1. When the suppression is 1/e, it starts to become really visible in effect. So for nearby sources, this effect of absorption of the EBM works at 20. Not really. This interaction of photons happens only at high energies. If we go a bit farther away, that's already at 0.2. A source of 0.1 is relatively nearby, right? But if you look at the absorption, you see that it becomes already affected at 1 TeV. So, 0.1. But we expect, if we believe in the steam model of the EBL evolution, we expect to have this interaction with the EBL already at the percentage of 1 TeV in the spectrum. And look what happens about 1 TeV. This absorption here explodes. So the photons are not a bit suppressed, but they are strongly suppressed. So our flux is, as we increase the energy, is more and more suppressed. So basically, we cannot see much of it. Tau is 10. You really cannot see a single photon, right? If you make the number, you see that the surviving probability is basically 0. So let's now try to go at redshift 1. Redshift 1 is the current limit for Cherenkov telescope observations of extragalactic objects. Why? Well, our threshold is 100 GeV. 100 GeV is here. Tau is already 1 at 100 GeV. So the flux is strongly suppressed already at 100 GeV if your source is that redshift 1. Okay? So you have here a lot of information that are all that are telling you two basic things. If you want to study the distant universe, you must stay in the low energy band because the suppression is very strong. Another one, on the other side, if you want to study the EBL effect, then you might play with lasers or with abstract objects and different redshifts and see what happens to their spectrum. Because absorption, tau 1, it doesn't mean that suddenly you do not have photons. It means that you have a survival probability of 60%. Your flux is suppressed by a factor of 1/8. So you still see photons, you see the deformation in the spectrum, and you can study the EBL. This is the same plot from another point of view. This is the line built assuming tau equal to 1. Okay, so this is the we are just looking now at tau equal to 1. how it evolves, this tau equal to 1, with redshift and energy. So for energies at 100 GeV, tau is equal to 1 and redshift 1. We have seen it before. If we go at 1 TeV, tau is equal to 1 already at 0.1. This is exactly what we saw before. And then what happens? Tau, it explodes. What is this? Suddenly it becomes that tau is equal to 1 basically here in our galaxy, very nearby. If you have an energy of 10 to the 6 gigaelectron volt. What becomes more probable as electron? What is the background in this case? That is so huge that you have energy enough to create pairs. Remember the relation between the energy of your TeV photon and the background, where we estimated that with a 1 TeV photon we have a 0.5 eV for the creation. So here you have 10 to the 6 GeV photon, then your energy is very low of the other photon. What is this? It's the CMB. Okay? So the CMB is the background on which our TeV very energy photon interact when they have an energy of 10 to the 6 gigaelectrons. Okay? So CMB comes into game in case of TeV astronomy at galactic scales, because we need electrons, and also because the cosmic depth is very, it becomes very nearby because the CMB is huge, is so big. So I would like to maybe 5 minutes. the third time. So. Okay, so let's restart. We have seen that the EBL is not as much known as we thought, probably, but still, we need it. And if you want to study propagation of gamma rays. So now I would like to focus on this fact that you have an intrinsic spectrum emitted that quite often we approximate with a power law. Then we have the travel curve, and then we have the spectrum that we observe that is deformed, the highest the energy, the highest the absorption, right? So we have three elements in this game: intrinsic spectrum, distance, and EBL model. So you can say, I know the distance of a source. I take an EBL model, I can estimate the intrinsic spectrum. I can deabsorb the spectrum, as Tommy has not mentioned a few days ago. And therefore, if I build this intrinsic spectrum, I can study the properties of the spectral energy distribution. And this is something that we do usually in our papers. We measure a spectrum, we assume an EBL model, we know the redshift here. In this case, Macarian 501 is one of the first emitters discovered at TD and has a redshift of 0.03. And then we can correct every single spectrum point by the factor that is related to the energy. Okay, and so we reconstruct the intrinsic spectrum. This process is named the absorption, because you put the EBL and you see what was emitted by the source. Here we have a source that is very nearby, 0.03, and in fact, you see that the EBL is acting only at higher energies in an effective way. Now, let's see the opposite case. One of the most distant sources ever detected, redshift 0.9. We have Fermi-Lacto data here, and then we have Cherenkov data here. Fermi-Lacto, you see, they have huge error bars. This was a transient event, so Fermi could observe only for a tiny fraction. And if you remember, the sensitivity for short observations of Fermi is quite poor. This is why we have these large error bars, even if the flux was pretty high of the source during this burst. And in this case, already at 100 GeV, if you try to estimate the intrinsic spectrum starting from the observed spectrum, you have a strong correction for these 3 points from 100 GeV, because this source is so distant that everything is played in a tiny fraction. All the effect of absorption is strongly effective already at 100 GeV. Below this energy, you do not need to correct because the transparency is not affected by EBL. You see that if you look at the horizon, you see that very nearly. Basically, below few tenths of GeV, you do not have this EBL process because simply the effect doesn't take place. And what we will see this afternoon is I will try with you to extract this data and try to see the data themselves, where you can get them, how you can retrieve Cherenkov data. Now we said we have 3 elements: intrinsic spectrum, EBL, redshift. We have estimated the intrinsic spectrum assuming a redshift and an EBL model. But you can also do something different. You can assume the intrinsic spectrum and the redshift and estimate the EBL, right? And this is how Cherenkov instruments try to constrain the EBL. They assume an intrinsic spectrum and they estimate the EBL needed to arrive to that intrinsic spectrum. So it's 3 elements. Depending on your unknown, you can use the other 2 to estimate the unknown. And it's a nice game because this gave the opportunity to set a stringent limit on the EBL. What happens if you correct your spectrum too much? If you take an EBL that is too luminous, then your spectrum show an upturn, like here, and it is not physical anymore. So usually what we assume as intrinsic spectrum is a spectrum that is a power law with the same shape than what observed at low energy, for example, in Fermi band. This is a sort of limit that we set. And with this in mind, let me go here first. Many authors have been able to see this band in the EBL as EBL limits. So this has been proven to be a really powerful tool to constrain the EBL itself. And the nice thing is that we are very close to the lower limits set by galaxy count. So what does it mean? It means that the galaxies that we see probably are all the galaxies of the universe. We do not lack much light because we are very close to this lower limit on the light set by the galaxy count with our EBL estimate. Let me mention now a specific case that is my favorite science case, that of extreme blazars. Extreme blazars are blazars, and I think that these are relevant also for your study, for which the band of the SED, of the spectral energy distribution, is not as in usual blazars at 100 GeV, but is shifted to 1 TeV or even beyond. This means that we have a lot of TeV photons in these extreme blazars. And also, if they are nearby enough, you can use them to probe this infrared EBL, for which you need nearby sources and a lot of TeV photons. Because the effect of interaction to probe the infrared is in the multi-TeV band. And this was for the first time discovered by the Haas collaboration in a very interesting paper where they used this extreme blazer to set a limit on the EBL. And with this work, they ruled out the claim of these population P stars because they set limits that were incompatible with this claim that was probably due to the instrumental effects, the background effects I was mentioning before. So this field of research is very active. Now the search for measuring the EBL with Cherenkov and Fermi instrument is collecting data, trying to put together all the different instruments. And yeah, there is a lot of work there. And now the main business, as Tomislav said, for other studies, is that of statistics, trying to find the better statistical method to combine data. It's not trivial. From the future, we have also in this case the right expectation for CTA, mostly because CTA will have a very wide energy range, a very good sensitivity. So with the spectrum measurements, we will be able to set more constraints, especially in the evolving EBL. I'm not able to play this. Now,
no, because it's connected.
okay.
Wait.
No, it's working. Yeah, I hear. Okay. So as one movie for you. Sorry. I don't know, it doesn't work. No, it's an example of a Fermi study on EBL. It was showing the photons, and now you have tertiation as a method to study EBL from a laser from actually more than 700 lasers they used, all combined together. And they were able, by putting all this data together, to trace this star formation history that is really measuring EBL from a section on the spectrum that I was mentioning before. Sorry, I didn't have to. This is again this plot. So you can use a lot of emitters, and Fermi can see up to redshift 4. And use the highest energy photons by Fermi, the ones at few tens GeV, to set constraint on the evolving EBL. And in this way, you measure the star formation rate. And this is what they did here in the paper. So really, gamma ray, studying gamma ray allows you to probe cosmological measurements in a completely independent way than other methods. Now the third game. So we said assume an EBL, assume, in this case, we assume EBL intrinsic spectrum, and we can retrieve the redshift of the source. Why is this? We should know the redshift of a source. That is not the case for blazars, actually. If you look at the 4-lab catalog, the catalog of Fermi blazars, you will see that a large fractions of blazars do not have a redshift measurement. And this is really a problem for us and for you, because if you don't know the redshift, you cannot estimate the absorption. And why don't we know the redshift? You remember the spectral energy distribution of a blazar. You have first peak in the optical, the second peak in the GeV. This first peak in the optical, in some cases, is so bright that doesn't allow you to see the host galaxy. That is the one from which you retrieve the redshift of a source. And therefore, you don't know the redshift. But this game of taking into account EBL, assuming the intrinsic spectrum, you can estimate the redshift of a source. Okay, now let's make it more complex, and let's add a magnetic field in this reproduction game. What does it happen? Where will be the magnetic field effect in this? Very trivial, eh? Don't think too strange. What will do a magnetic field? The gamma and magnetic field is no. The gamma, but then we have electron and positron. Yes.
And it's big because one is both, one is negative. So the electric will go one way, the one will go another.
Exactly. And this is an effect that must take place because in the universe we have a magnetic field, right? So this magnetic field should deviate our pairs and open them. The next thing, or a bad thing, depending on the point of view, is that this intergalactic magnetic field is largely unknown by an order of magnitude. We really don't know what the strength of this magnetic field is. So, depending on the strength, of course, you can imagine that your deviation will be stronger or smaller, and not only depending on the strength, also depending on the coherence length of the magnetic field. So this idea allows some researchers to propose, why don't we use then observations to probe magnetic field. How do they do that? Well, the point is that if you deviate electron and positron, let's assume you deviate, then in any case, you might have an interaction with the cosmic microwave background of these electron and positron pairs. And if you scatter the CMB, you will have a secondary gamma that has an energy related to the primary energy of this photon. And therefore, you have a secondary emission at lower energies. So you have primary gamma. Some of them arrive to Earth, 10 eV. Some of them create pairs. They are negated more or less. And this pair can interact with the CMB, scattering to higher energy. Therefore, you will have your primary emission, but also, in addition, a secondary emission. If the magnetic field is very strong, then this secondary emission will be very large. So the size of the secondary emission strongly depends on the strength of the magnetic field. Also, the strand, the clearance length, make an effect on the delay, on the time delay of this emission. Okay. So, this must have an experimental effect that we might want to measure. One way is to study the spectral deformation. You expect that depending on the strength of the magnetic field, you expect this pre-process emission to have a band at lower energies, because these are the upscatter CMB photons, like this deviated electrons. Or you want to look for an extended emission around your point-like source, again at lower energies. Okay? So these are the two lines of research, or you want to test for a delayed emission, but here I think that it's less promising because the time scale are probably longer. So these are two ways, active ways in which we are trying to constrain the intergalactic magnetic field with gamma ray data. And these are the current limits that are actually quite stringent and used by the cosmological community. In the future, again, we are going from this sensitivity here to this CTA. So CTA will really probe this re-emission at lower energies. Also because the PSF of CTA will be much better, the point spread function. Now the last fact that I would like to mention very briefly in the propagation is that we have a case, more than one case in Fermi, just one case at TV, of gravitational lensing impacting gamma ray data. And the fact that we have observed is very, is the standard one, a delayed emission from one, there was a flare from a source. There is a lensing galaxy, and therefore this flare is seen as a prompt flare and then a delayed emission. And this is indeed due only to the lensing galaxies that is between us and the emitter. So what happened here again, remind you the story of how we observe our technique. Fermi, thanks to the fact that every few hours you can see basically on the sky, it detected the flare. Okay, this is Fermi. And then after 11 days, he detected the delayed emission. He told us here, look, there is a flare. Well, imagine not only, but we were in moon time. So moon timing for us. But after 11 days, the moon was not there. And we could observe only the delayed emission and thought that the delay was exactly as expected and observed in the other bands. You see also TBA is an optical telescope couldn't observe because of. So this is just a mention of other propagation effect. In summary, about the extragalactic distances, it took me a while to show you, but I think it's worth to understand some details of the EBI, because it is the subject that is most related to your case. And what I said is that, well, indeed, EBL affects the photon propagation. It is poorly known, but it can be used as effect of interaction to study cosmology and test EBL model. Moreover, intergalactic magnetic field can also be probed with our gamma ray observations. Finally, I show you a case in which there was gravitational lensing affecting our observations. The experimental perspectives are extremely bright in this sector. On one side, CTA will have better spectra, better widespread function, and on the other side, we also have a LASO with its highest energy part extension that might be very useful for nearby sources. Let's come now to the galactic distances. Yes, seen already at galactic distances, maybe CMB might play a role, but only at extremely high energies. What happens at lower energies? Well, let's focus on the radiation field, and let's ask ourselves, the process is always the same. We have a gamma at high energy, the gamma of the target, and we want to create, and we create electron positron in order to have this propagation effect. What are the diffuse background in the galaxy relevant to this process? The EBL inside the galaxy is faint. We have seen it already. It doesn't affect until very high energies. But very recently, there was a study about the light of our galaxies. The galaxy is very bright in optical and infrared light. We have stars, we have dust. And what this author studied is the contribution to the survival probability of the infrared light, mostly inside our galaxy, produced inside our galaxy. And you see that this might be effective, but only at high energies, here than the CMB that we have seen. So in our galaxy, the light from the infrared light from the dust might indeed imprint the spectrum of galactic source. And then there is a problem. The galaxy is not uniform because we are inside it. So depending on the direction you're looking at, you might have more or less absorption. If you are looking through the galactic center to a source far away, then the probability of interacting with this infrared is much higher than if you are looking close to you, right? So this makes things very complex in the study of galactic sources because you want to know really the real path that the photon did. And I think this will be much more explored in the near future. Let's come now to the propagation beyond the standard model. So we have seen the standard scenario. Basically, we have electron-positron production on diffuse backgrounds. Now, what's happened if we have quantum gravity effects? Well, I will just mention a couple of results because I think that Tomislav covered this very well already. So let me just briefly sense and remember that we have many lines of studies of quantum gravity effect, like time of, but I will show you two examples of time of flight studies and modification of gamma-gamma cross-section. These are the current limits. If you are curious, there is this very nice paper that is summarizing all the results in addition to the review that I mentioned before. So let's see yesterday what happens to our optical depth if we have a modification of the gamma-gamma solution due, for example, to to quantum gravity effect. Then this is the standard EBL tau, the absorption. And this is the modified absorption according to a specific realization. What does it mean to you? What would you test then? In which source would you search for these elements? If you want to see some deviation from what you expect, you need to go at least 10 TeV, right? If you have a nearby source. And the same if you have a nearby. And well, you have to go at higher energies. You have to see this. Sources that are possibly a bit distant, but especially that you can observe until tens of TeV. And this is one example of a study of the modification depending on the different realization of the LIB. So this is what you would expect. Instead of a suppression of the flux, you have a suppression that, and then you do not suppress anymore in the flux. So what you expect is that you have the flux measure, you have a hole because the photons are suppressed, but you have again photons. This is true only if the primary emitter is emitting these photons. So you need emitters, if you want to probe this, in fact, you need a emitter that give you photon up to 10 C. That is not anything fast, because lasers here, an intrinsic cutoff in emission. Maybe there is some hope in these extreme lasers, because their emission is shifted. But the extreme lasers are so faint that it's very difficult to make this search with the lasers. So another possibility is to use more nearby sources. Well, these are the elements for you to search. Then we have another class of searches that are the time of flight studies. As we mentioned yesterday, depending on if you look at n equal to 1 or 2, you have different expectation from the dependence of the time variation and the redshift. You know? And what you want to see, if you want to do time of flight study, you need the fast variations. Because if you don't have variations, you cannot really constrain this delayed emission. You need at least a shape in the variation. And this is already something difficult to find. Then you need statistics, something bright. You need photons if you want to probe, especially with a good statistical method. You want the distance because the effect is proportional to the distance. You want to have an energy that is higher as high as possible because these effects are more evident at high energies. So this again are the conditions that will drive your observations or your search for data if you want to probe your field. This is an example of a data set in which this was studied, already mentioned. You see, this is a light curve from a nearby laser, again Mark 501. And there was a quite fast flare that magic detected with a doubling time of 2 minutes. So the source is light, relatively nearby, the flare, so more photons, and especially a short flare. So this allowed the collaboration to test some theories to make a study of the time delay. But don't look at this plot because this might be might give you the idea that there is a delay, right? Here we are rising in energy from the band 0.15 to 0.25 TeV up to above 1.2 TeV. This seems to be a sort of trend. The point is that when you study these things with the proper statistical methods, that is the maximum likelihood. In fact, you put in the game things that you do not see with your eyes. don't trust much your eyes in this study, but you must use statistics. But it is not an easy job, as Elena always know. But these indeed are the kind of measurement that we need if we want to prove this effect. Fast variations from distant objects and bright. And then you must learn the proper methods to analyze the data. It's not just enough to estimate the peak and then see if you have a peak sheet. It's not like that. Otherwise, you will turn it into a paper that cannot be trusted or even published. Anyhow, if you're interested in dealing with very energy data, you should know that we release the data to the community depending on the source. I will show you some examples this afternoon. In any case, this is also something very important for the future generation, because you have seen there is a transition in our community from particle physicists that have their own data to more astronomer that collect the data and release not the final data, but an intermediate data with the software packages. We are not there yet with this, but we will be, or maybe your action can build this in the future, trying to work on the release of not final data, but intermediate data, so that you can have and also adding a software, so that you can play safely with the data without just looking at the big sheets, but putting inside and having also all the needed information on the instrument, observation, the condition, the bias, and things like that. And this is what is probably needed from a growing community, not only for you. You will see it's the same for us on light particle physicists. They are doing this support, and this is the future. So my suggestion is, even if you don't feel an experimentalist, don't be afraid of data. You can learn data analysis, especially the one that see that it's not available, but will be. You can learn and try to make your own study with the data, because it's much more solid also. It takes some time, but I think it's worth for the near future. Now, some final words on axions. Another way in which we might, that was proposed as a modification of the propagation, are axion-like particles. You are probably more familiar than me with these particles. These are pseudo-scalar particles proposed to solve the strong CP problem. They can actually decay into 2 photons. And axion-like particles are a generalization of the axions, and they could play an important role in cosmology because they are a possible solution for the dark matter problem. Now, why are we interested in axions with the propagation? Well, as I said before, they can decay into photons, but especially an axion can oscillate into photons. You might have a photon oscillating into an axion or axion-like particle, and then this axion go back or not into a photon. This means, well, the axion doesn't interact with the EBL. So if you have a photon oscillating into an axion and then it goes back to a photon, you will see more photons than expected from the EBL process. Right? So this is a possible deviation from what is expected. So if we see more photons than expected, that could be due to axions. Right? But it is not as simple as this. To do so, to do this process of oscillation, you need a magnetic field. And the strongest is the magnetic field, the more probable become this oscillation. And the intergalactic magnetic field is probably not very strong. In order to understand the current researches, I must introduce the concept of critical energy. So we said that depending on the magnetic field and the coupling constant, there is a critical energy that if you are below this energy, then the probability of photon mixing is suppressed. If you are well above this energy, the critical energy with your photon, then the probability becomes feasible and the mixing photon and output is maximum. If you are around the energy, then you have distortion that may affect your gamma rays. Let's see what does it mean in terms of search for evidences. So, in case of you are well above this critical energy, then you might have an observable effect in what I said before, in the absorption probability. You might see more photons than expected because you have this oscillation of photons in one that, in a way, prevent EBL to play a role in the propagation. Instead, if you are around this critical energy, then you might have energy-dependent distortion in the spectrum. Let me show you an example of this last thing. Energy distortion, these are data, gamma ray data. You see that you expect, let's say, you assume that the spectrum is a power law, and you see a deviation from this power law. Then you study how this deviation, these wiggles, okay, are probable depending on your theory. In this case, the nice thing is that the Fermi concentrated on the AGN and GC1275 because this source is in a galaxy cluster, and in galaxy clusters, the magnetic field is much stronger than in extragalactic space. So your probability of action playing a role acting to these photons just after the emission is much higher than during the propagation. This paper, I found it yesterday. It is still to be published, but it is in the future. So this is one way of searching axioms. We go through the spectrum. The other way is seeing more photons unexpected due to the fact that the EBL is less effective than expected. And this is a nice example on how difficult it is to use properly statistics and statistical methods in our studies, because in 2012, two authors published a possible hint for detection of this deviation because they were seeing photons, unexpected, too many photons in their opinion, with a tau of larger than 2. So tau is how we suppress the spectrum. If you see many photons at tau 3 and 4, it means that the probability that you expect is not the real probability of these photons to survive. So maybe it is a hint of accidents. This was their proposal. But then other authors said, look, your study is nice, but you didn't take error bars. If you weight your data with your error bars, if you take into account errors, then your evidence becomes not significant. And therefore, the claim was somehow is not anymore. We do not have any hint of anomalies once we take into account errors. Very often in our spectra, you see that the last point, once you correct for EBL, it goes up. No? And you think, wow, but this is unphysical. Probably there is some hint of new physics. No, if you look at the error bar, usually this error bar is huge. It's difficult to reconstruct a spectrum if you have just a few photons, like in our case. So always, I don't know, maybe the best thing is to speak with with people like Tommaso Dorigo when you make a study, especially if it is a new study, to be sure that your statistical framework is solid. Because from from one side you want to make a big discovery, from the other side it's not nice if your discovery turns to be false. So really statistics is extremely important in this field of new physics. And this is a compilation of the current limits. This is what I was saying before. In the art community, they are collecting the data and make it available to the world in a repository so that everybody can plot and play with for now with the limits. In the future, it will be with the data. So it's an ongoing effort. And this is the region interested in the gamma ray. So gamma rays are somehow complementary to other experiments. The most famous is CAST. I think. Yes. CTA is about its possibility of probing axion-like particle effects, or at least constraining the parameter space with data because of the high resolution spectrum that they expect. This is an example of what are the expected capabilities of this future experiment, in which for sure you will be more and more interested. Okay, so let me make a few concluding remarks, just to have a final overview of this topic of propagation. We have seen, first of all, the standard model of propagation. The photon can arrive to us, or we can produce electron-positron pairs mostly on the extragalactic background light. And this effect depends on the energy. It can be used to study the emitter, but also to study the EBL or constrain the redshift of a source. Then we have seen that the magnetic field might also be constrained by this effect by measuring the deflection and then reprocession of gamma rays at lower energies. And this might be studied with maps trying to search for an extended emission around objects. Then we have mentioned the galactic case, that is relatively a new field of search that will be in the galaxy, and it's quite complex due to the fact that you become sensitive to the direction in which you see. So further studies are for sure to come in the near future. Then we have seen that LIB, or in general quantum gravity, in fact might give signature of time delayed emission here in the photon propagation, or might affect this electron-positron threshold. Finally, we have seen that we might test some theory of oscillations, gamma oscillations, by looking at the highest energy photons or at the wiggles in our spectrum. All these together make a sort of overview of the gamma ray propagations. And as usual, I think I was stressing enough that you need to know many different things to make your study valid, including also the instruments and the data. Knowing the data, the instruments is important, even if you are not an experimentalist. And okay, I will stop here. Thank you. First one or the afternoon?
That's not say there is a, I don't know, it's a,
For the moment, no. But really, there will be a jump in sensitivity in the near future. So I'm not pessimistic about it. The expectation are so that we are going to go and large economic space. And also, of course, there is also the problem with the discovery bursts that are the most promising in terms of photons and so on. We need some luck to get the data to get a good sample of this burst. But I think that in this sense, the numbers problem that we are doing our best on the experiment. The number of GRBs now very interesting every more since 2018. That's because we really optimize the repointing system, and therefore there is large room for
CPA and LASO will complement each other.
Yes, what's CPA on the short time probably is much more important than LASO, but the LASO energy is huge. And also, I don't remember, but I think that also the constant function of LASO is much more expensive. So they will be really complementary. We need also south LASO. Now LASO we see half of the sites, here we have two sites. So maybe Sweden will be one. It's not funding. So we for the moment with LASO we are already only for the events. Yes, especially at extremely high energies. But I don't think that for this for the extragalactic sources, this is really relevant. I don't think you think you will see a power from an extragalactic source. It's unlikely. So it optimizes CPA so that you are better in the galactic star, so higher energies in the south.
So thank you very much.